I'm Weronika.
I'm Chris.
I'm Riley, and this is our water maze project. Basic concept here is we made two mazes. This one obviously with a more simple path, kind of just around and out the bottom right side. This one much more intricate with plenty of wrong paths for the water to take and get stuck in the crevices. But we plugged this end here with a paper like this and then dumped colored food dye. This one was blue and this one was green in the trials. So the water would get stuck up in this reservoir, and we used the dimensions here to calculate the volume. And then when we pulled the paper out, we started a timer and they raced each other through. Underlying concept why they can get through is gravity pulls it down in the beginning, and then there's air in all these pockets, so it has nowhere to flow except the other way out. But some water does get stuck, as you can see, in the wrong pockets.
As you can see, the blue fluid consistently wins each trial. While this is partially due to the path being 2 inches shorter, the main cause is the longer path exposes the green fluid to a greater friction force, leading to a decrease in exit velocity. The friction also causes head loss, which, as we know from the energy equation, results in a lower velocity as well.
This was our experimental data, and as you can see, the path distance was in fact 2 inches shorter, and it did end up coming out quicker in the blue side than the green side. And these were the dimensions, so they were the same for each maze of the reservoir holding it. And based off of the data that we found, we calculated volume of the water passing the by multiplying all of the reservoir dimensions, and then to find the volumetric flow rate, which is V dot, it was dV over dt, and V being the volume of the water passing. And then we took the average of the Q for all our Q values for all 5 trials, and this is all our data here.
For our model design, we use SolidWorks to make both of the models, and then we use 3D printing. We used a PLA filament to print these, and then for the top cover, we used 1/8 acrylic, and then glued them together with silicone. The dimensions of our mazes are pretty small, and this is because the channel size does matter in this case. The smaller the channels, the better the surface tension will work in the maze. And we did try a few different glues, and we figured out that silicone spreads the least and makes the most airtight seal.
So some of our takeaways is, obviously, we just said the size of the maze channels impacts how the water behaves. Basically, the smaller channels, greater surface tension, and more pressure will guide the water to the exit.
Okay, another takeaway is that when deciding what materials you're using, you should make sure that they're able to be glued together, and picking a glue that doesn't dry too fast and is thick enough to prevent any air bubbles from forming.
Lastly, another takeaway is you have to think about how the water would be held in the reservoir before releasing it, as we had like a little bit seep through the paper